Hello, everyone. Here are my updates for today. So just a quick recap. Last time I was talking about concurrent kernels, which is for a mixed sparsity tile, we can launch two programs for each output tile. One of those programs will process the sparse tiles, and one will do the dense tile computations. And here's the pseudocode. So as you can see, we check the second dimension. If it's 0, then we will compute the sparse row results. If it's otherwise, if it's 1, then this program will compute the dense results. So the computation kind of looks like we go through the key dimension and we compute the dot products and then accumulate the results into our accumulator. And in the end, we automatically add our accumulation into the outputs. And we'll do it for both of these kernels, for both of these programs. So the first thing I want to talk about for today is some results comparisons between the sequential and concurrent kernels. So here are the results. I've run it for many different sizes. So as you can see, we have the matrix size M and K, and as well as sparsity levels, and then the performance for sequential as well as concurrent. So we can see that most of them has the sequential is performing better than concurrent, but there are some instances where concurrent is performing much better than sequential. So here are some stats. On average, the sequential performs better than concurrent by around 0.2 teraflops, a maximum of 2.7 teraflops, but also for one specific case, it underperforms the concurrent one by up to 8 teraflops. Here are some more results, just to show that most of the time, sequential performs better than concurrent. And there are some instances where concurrent does otherwise. And just to note, all of these are using auto-tuned configurations, so that they are the best configurations, the best tile size that we can use. And they're also run on RTX 4090s, sorry, RTX A4500s. So the next thing I want to talk about is varying tile size. So motivation. So through auto tuning, we saw that there are different optimal tile sizes for sparse and dense tiles. So maybe for sparse, we may have a rectangle tile that's the most optimal, whereas for dense, we might have a square tile. Right now, we're only able to use one tile size to process both sparse and dense in a row. And our goal is to see if we can achieve better throughput if we allow the sparse tiles to use an optimal sparse configuration and the dense ones to use the optimal dense configuration. So just an example, here we have a case where the optimal dense tile is 2 by 2 in the A matrix as well as 2 by 2 in the B matrix. The difference here is now we also have a sparse tile, but this sparse tile is a rectangle in the A matrix as well as the B matrix. So in this case, the M and the N stays the same. The only thing that changes is how big the tile is in the K dimension. So instead of 2 for the dense ones, the sparse ones will be a multiple of that, which will be 4. So this is one of the examples. We can do something like this, and eventually we'll get the same results for this square output tile. The other example that we might have is a bit more complicated. So we can also have maybe the sparse, if the sparse tile is a rectangle in the nth dimension, then we would have something like this. And this is a bit different from what we've had before. So we cannot just go from left to right and accumulate for the square tile that we have before. So we have to come up with a different approach to address this. So what we can do here is we can think of it as two different input matrices, one for sparse and one for dense. So as you can see here, we have the A matrix, and we can kind of mask our tiles onto the matrix. And imagine this is our dense configuration. So now we can divide it into 16 pieces. And imagine our sparse tile configuration is 4 by 2. And this lets us divide it into 8 pieces of sparse tiles. And after that point, we can compress this matrix into our dense tensor as well as its metadata. And we can do the same for the sparse tensor. So something to note is that, let's say, let me get this. Let's say this is a sparse tile. So in this case, we would only be, we would have this in our compressed metadata. And let's say these two are dense tiles. So we would not have this dense tile as a part of our compressed metadata here. So in a way, we're not really duplicating any data. So using our dense and sparse matrix now, we can multiply them by the B matrix. And with that, we will output something like this for the dense and something like this for the sparse. So each of them would have calculated respectively their own work. And in the end, with this, we can atomically add to the output tensor. So for the next steps, I'll be implementing this kernel like I mentioned before in the previous approach. And I also want to use an auto-tune config to see if we actually indeed get better performance from this, or if there's something else that we should try. So thank you so much for listening, and please let me know if you have any questions.